Hmm, I am coming live, going live. I think I'm live on Twitch, and yep, and I should be live on YouTube. YouTube takes a little time to be updated, and yep, I'm live on YouTube. And let's go. That is crypto and things. Okay, machine, modern assembly language, not machine language. So yesterday we did some things. We wrote a program that would take two 64-bit numbers and find their product and print a 128-bit number on the screen. And that was a crazy program. It took us 2 hours to write it and debug it and make it run properly, but still in the end we couldn't get it to work. But the logic that we used to multiply two operands was the same um, that is used in the book. Okay, and which part was it? It is right here. Yep, this part. So here they used a normal multiplication to get the least significant bits and a unsigned multiplication high to get the most significant bits of that 128-bit number. So now we move on to division operations. Operations which we can use to divide things, divide numbers. There are only two division instructions in AArch64. Okay, signed and unsigned, signed divide and unsigned divide. Destination register M and N, two registers that you provide which have the values that are supposed to be divided. The value in this will be divided by this. Okay, the OP is either operation is either signed division or unsigned division, and this is what happens. Divide the value in this register by this register and then put that value in here. That is it. You need to know about division. Now we move on to comparison operators. These three comparison operators update the p state flags but have no other effect. That is crazy. We can use these to find conditions like comparison. If something is equal to something, then this, and we can then use that logic to apply to make loops, for loop, while loop, and stuff. Compare negative. Test bits. Test. They each perform an arithmetic operation, but the result of these operation is discarded. Compare is an alias for sub sign, and CMN, compare negative, is an alias of add sign, and TST is an alias, test bits is an alias of and sign. No, S means update the flag, and here also S means update the flag, and TST also. The S at the end of these add, sub, and instruction signifies that they will update the P state flags, which is in the P state register. Now, operand 2 can be operand 2, like we saw before. It can be multiple things. It can either be a register value or an address or an immediate value. I don't think this can be an address. This can be an immediate value or a register whose value will be used here for comparison. Now, op is one of comparison negative or test bit. Compare this minus this, the first minus the second. That is what the comparison instruction does. And compare and set p state flags. Okay, compare negative. So it will add these two and compare negative and set p state flags. Then test bits. It finds the and operation, test bits, and Set P state flags. Okay. Test equality. It finds the XOR of these operations. Test equivalence and set P state flags and set P state flags. Okay. So test equality. Um, if they are not equal, then this will give 1, and if they are equal, then the output would be 0. Now compare. Yep. Now compare the contents of this and the value this. Compare this to this. Okay. Compare the contents of the second register and the third register, but sign extend W. Compare negative. Yes, compare negative. Second, to sign extend W set flags. To sign extend W and set flags. This will be extended because X signifies here 64 bits and W signifies 32 bits. So this 32, shit, this 32-bit number will be extended, sign extended, and will be made into a 64-bit number, which will be used for the comparison. Shit. Mouse functioniert nicht. Aber es funktioniert. Aber jetzt es funktioniert. Now test bits. The contents of the 32 bits from the W1 register and these. Okay. Example 10. The following listing shows how the compare, branch, and add instructions can be used to create a for loop. Interesting. There are basically three steps for creating a for loop: allocating and wait, how can we create a for loop? To create a for loop, um, we will compare one thing again and again, and yeah, first we initialize, then we have the compare function that is so for this initialization, we can use the move instruction to move some value into a register, and then for this we will be using compare and then a branch operation. And for this, we inside uh, the label that we will be calling by the branch operation, we can do update the contents of the register which we used to store the value by 1, increment the contents by 1 every time. Now, there are basically three steps for creating a for loop: allocating and initializing the loop variable, testing the loop variable, and modifying the loop variable. In general, any of the registers from 0 to 15 except 8 can be used to hold the loop variable. These are the scratch registers showed in Figure 3.2, Section 5.4 in Chapter 5 will introduce some considerations for choosing an appropriate register. For now, it is assumed that x0 is available for use as the loop variable in the example. Suppose we want to implement a loop that is equivalent to the following C code. The loop can be written with the following AArch64 assembly code like this. Okay, this is initializing int I equals 0 in the 0th register. Okay, and this is what is inside the loop. The loop sees if compares the value 10 with the contents of the 0th register and BGE that is greater if the value this becomes greater than this, that is if it becomes 11, then we will go to end loop. What that is what should happen before the loop. Then here we have the instruction for the body, and here we have add W, add 1. We will add 1 to the contents of the 0th register and save that value to the 0th register. And then we will just branch back here where our compare operation will run again, and we will try to see if we can branch to the end loop again. Okay, example 11. The following C program waits for the character A to be input on its standard input. Okay, and when void, you don't have to use void there. Do nothing. while get char is not equal to a. Okay, and then return 0. Okay, so this function does not do anything. Let's try to write this function in assembly language on our own. And chapter 4.s. This is the code that we wrote yesterday, and let's just comment it out and begin writing our new code. That is in the dot. Do we need something in the dot data section? Well, yes, we do need something in the dot data section to store the variable that has been provided to us by the getChar function. Okay, so in dot data, we will store a character which will give us a byte, and the byte will initially store what? 0, let's say. That is the value that it stores initially. And then in the dot text section, we have a something called global and something on my screen. And then we can align like the good people that we are. And then we can define the main label. The main label, what does it do? Okay, I have to have a point. Okay, first I will get, okay, first of all, store the frame pointer and the link register onto the stack. First of all, just good, that is just what good people do. And that is store pair, store the contents of the 29th register and the contents of the 30th register onto the stack pointer. But in minus means increase in stack because stack grows downwards, as you know. And then after storing the stack pointer, we would we have some place there to get char function. We will be providing um, the output, a place, a location, a memory address to the get char function in the 0th register. So then now we should load the address of the char label that we provided above in the 0th register. For that, we'll get address of the page in the 0th register and who's the char. And then we will add to that the offset, the page offset of the char label. And then after that, now we have it. Now, okay, now I think the loop should begin. Loop, um, which will first get the value in the from the 0th register, which will get the value of the memory location whose address is in the 0th register. For that, we'll do LDR the contents into the first register whose location is in the 0th register, and then it will compare the contents of the first register with 65, right? We have to do the loop till you get A, capital A, and capital A is 65. Now we compare it with 65, and if it is not 65, B not equal. If they are not equal, wait, if they are equal, then I branch off to end loop. But if they are not equal, then just move on. We call the get branch function again get character function again. B get char, right? Get char, we get the character, and then after getting the character, we just branch again to the loop, right? And here we have end loop. What would happen after it? And end loop would just first it would move some value into the zeroth register, and the value should be, let's say, 1, 2, 3, 4, or some imaginary crazy value, and then return. Now, the only problem I think we could get in this is when I call the get char function, the return value that it uh, sends us is stored in the get char function. So that might cause problem. So what can we do instead of that? And so what we can do is, I think that is all we can do. And if it does cause problem, then here instead of directly loading the value here, we can load the address again and then check the value. Let's see. Clang chapter 4 and the output should be out. Okay, it works. B segmentation fault. Yes, that is the thing. The fault. So I think that is the thing causing the problem. That when we call the get char function, it updates the zeroth register so that we no longer have what we in the zeroth register no longer stores the address for the char label. Therefore, every time before checking the value in the memory cell whose address should be in the zeroth register, we first load that address in the zeroth register and then we check. Now this might work, actually might work. Okay, still some segmentation fault. Okay, okay. Segmentation fault is probably being caused by this, but why? End loop, ENDLOOP, end loop, that works, should work, and then get char here. Maybe the get, how does it take function? Does it want its thing in the address it wants? Does it want it in the stack pointer? Well, if it does want the address in the stack pointer, then we can just do this. We can just, so we want 2 bytes, 1 byte to store the actual character. No, we have the byte here, and we load the address here into the zeroth register. Now we can store the address on the stack pointer. How do we do that? Store whatever is in the zeroth register in on the stack pointer register's location after adding 1 to it. After adding 8, our register takes 8 bytes. Shit, that is crazy. And now the stack pointer points to this, to the address. Now, I do not, I think this should work now. Maybe, I don't know. But then at the end, before end loop before everything, I reset the stack pointer by load pair into the 29th and the 30th register by stack pointer and adding 16 to the stack pointer. But before that, I have to no, I have to add 8 to the stack pointer and I store it in the stack pointer and add 8 before I even ran. Okay, I got a problem. Okay. This store is good. This function str stores the value of the zeroth address, which is the address of this thing onto here, right? That is good, makes sense. Before I even ran, I call this again. Okay, this is causing some problem, and this should not be causing some problem. Yeah, this should not be causing some problem. Stack pointer contains the address of the top of the stack, of the bottom of the stack, and then I add subtract 8 to get 8 free bytes, so that the stack pointer now points to the lowest, and I have lowest byte of those 8 bytes, and I have that byte and 7 more bytes above it to store the contents of the zeroth register. To store the contents of the zeroth register there, and this should work in that case. And then what am I doing? I am loading the value of the memory location whose address is in the zeroth register. Okay, that makes sense. Whose address is in the zeroth location, and that is char. So I'm loading the value char, which is initially 0, into the 1, and then I compare it with 65. And if they are equal, then I end the loop. Otherwise, I do get char with zeroth register containing the address and the stack pointer also pointing to the address of the char, and then I loop back here and then I check again this thing. Before doing that, I can load load contents into the zeroth register from the location whose address is at the stack pointer. That also makes sense. Clang bus error. Bus. So what about railway? Chapter 4. Well, let's see how it is done here. Okay, they store these like good people that they are. Then they use the 19th register to move the value. Okay, they store. Uh, okay, they are using 8 plus 8, 16 bytes to store these values, right? And then they add this to store the location of these into the 19th register, and then they move the value this into the 19th register. Why did they do this part? Oh, they store whatever is the value at the 19th register so that they can maybe at the end, yep, um, at the end getting the value. Well, they are getting the value to the 20th register, which they stored in the 19th register. Yep, that is also maybe good. And then they BL, uh, 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 L, I don't know, lang, how are they providing the out input to the get chart, call get chart to get the next character in the zeroth register. I'm just so stupid, just so stupid. I don't need this. The character I want, I will get it in the zeroth register. I need none of this. Shit. Uh, shit. Shit. Okay, so I call getChar to get the input into the zeroth register, and then I have to compare that. CMP compare the contents of the zeroth register with 65 and branch. If they are equal, branch to end loop, else branch to just loop, and then clear this stupidity. This should work now. Okay, okay. A should not work. Capital A, yes. And to get the return exit value, return value of the last function, I will do this. And you get 164. Okay, again 164. But I do not want 164. I said I want 420. Why am I not getting 420? This is not hexadecimal. This is pure 420. Clang, clang it here, and then echo and 164. Ah, crazy. Now, conditional operations. So how did they do it? They first get the character, get char, and then compare the value a, capital A, and the return value of the get char function. And if they are not equal, then they loop. That makes sense. Otherwise, they load back the value from which they stored onto the stack. I think this and this, this part and this part can be removed, and instead of using this register here, they can directly use this value here. It would work. Now, conditional operations. These conditional select operations set the destination register to the first operand. These conditional selection operators operations set the destination register to the first operand Rn if the condition is true, and to the second operand optionally incremented, inverted, or negated if the condition is false. Okay, conditional select, C select, conditional increase, select increase. Okay, conditional select invert, conditional select negative. There are five aliases that are derived from the previous instructions. Conditional select, conditional increment, conditional invert, conditional negative, conditional set, conditional select and set, and conditional set mask. Conditional comparison instructions allow P state to be set to either a comparison, conditional comparison uh, allows comparison conditional comparison instruction allow P state to be set to either comparison or an intermediate or an immediate depending on the flags in P state. C compare conditional compare negative. The conditional compare and compare negative instructions check the P state flag for the given condition. If it is true, then it sets P state flag to the comparison of Rn and either Rm or immediate 5 and either Rm or immediate 5. If it is false, it sets the P state flag to an immediate 4-bit value representing null. Okay, if it is true, then it sets the P state flag to the comparison of Rn, P state flags to the comparison of Rn and either this or this. Okay, it compares the value of the Rn register and this if the condition is true, and if it is false, then it puts then it sets the P state flags to an immediate 4-bit value, immediate 4-bit value, which represent negative 0 CV, negative 0 carry overflow. Now here we have option one. Option one is one of conditional select, conditional increase, conditional select increase, conditional select invert, conditional select negative. Option two is one of conditional increase, um, conditional increase, conditional invert, or conditional negative. Option three is conditional set or conditional set M multiple mask, set mask. Now this takes destination register, this and value. And this takes conditional. Okay, so conditional select stores value of this, stores value of this into this. Otherwise, if the condition is false, then the value of this increment or something into this. And conditional increase, uh, inverse or negative stores the value of this into this. Uh, if this condition is true, then they store the value as it is. If it is not true, then they do the increase or inverse or negative or something. Now, these things set, C set and C set. If condition is true, they set the register to something. The con is any condition, is any of the codes from table 3.2 on page 59. Okay, the negative 0 carry and overflow is a number. No, C compare, conditional compare, compares the value of this and this, and then sets them based on this. Okay, if the condition is true, they will just set them, compare them as they normally would, and if it is false, then they would put these values. Is any number k 0 to 15. The immediate 5 is an unsigned 5-bit immediate. Now, conditional select, it would store value of one register if the condition is true and the value of another if it is false. If condition, then Rn is stored in the destination register, else Rm is stored in the destination register. Now conditional set increase. If the condition is true, Rn is stored, otherwise Rm plus 1 is stored. If the condition is true in inverse, then Rn is stored, otherwise inverse of Rm is stored. If it is negative, conditional select negative, and if the condition is true, then Rn is stored, otherwise negative. Oh, negative is inverse plus 1. Inverse is 1's complement and plus 1 is just negative 2's complement. Now, conditional increase. This would conditionally increase the value. If the condition is true, then stored 1 plus into the destination register, and if it is false, then store it as it is. And for negative, if the condition is true, store the negative, otherwise store the value as it is. No, that is for inverse. And now if it is negative and true, if the condition is true, then this command stores the negative of the number. And why is this considered the negative of the number? Because this is one's complement, and adding one's one to the one's complement makes it two's complement, and two's complement is used to represent negative of a number. If the condition is false, then the value as it is stored. Now, condition set. If the condition is true, 1 is stored in the destination register, otherwise 0. And now, condition set m. If condition is true, then whole one, highest value possible, otherwise lowest value possible. Now, C compare. If the condition is true, then the flag, this minus this, contents of Rn register minus the contents of Rm, or a 5-bit immediate value is stored in the P state. Otherwise, the thing that we have provided is stored in the P state. Now, conditional compare negative. Addition is stored if the condition is true, and if it is false, then what we have provided is stored in the registers. Flip flop, crazy. Examples, conditional select this thing. Now, conditional select this thing. What does it do? This is a condition greater than. So if the contents of this are greater than the contents of this, then the contents of 1 will be stored into the 0th register. And if not, then the contents of second register will be stored in the 0th register. Now, condition select negative. If negative, not equal, not negative. If uh, third and fourth register are not equal, the contents, the things they contain are not equal. Are sorry, if they are equal, then the contents of the third register will be stored into the second register, and if they are not equal, then whatever is the value in the fourth register, its negative will be stored in the second register. Now, conditional inverse. If high, if high, what does conditional inverse mean? If high, if this condition is true, then the exact content of seventh register are stored into the ninth register, and if it is false, then the inverse of the content of the seventh register are stored in the ninth register. Now C set if equal if equal is true, equal condition somewhere somehow is true, then uh, x1, the first register, is set to 1 and otherwise 0. Now see compare, conditional compare. If mi condition is true, then the comparison of these and this 31 determines what will go in the p state register. And if it is false, then this thing, this 0b, signifies that the next characters are binary. So these 4 bits will be used for NZCV in the P state register. The following C function will flip the parity. Parity is mm, parity is the amount of ones I think a binary number has. Will flip the parity of a number and alternate between two values if the output is reused as the input. Will alternate will flip the parity of a number. Okay, that is just find the negative, I would say, of a number and alternate between two values if its output is reused as the input. Okay, and flip-flop. If it takes in a number, if in number division by 2, that is even, then it returns number 1 plus 1 to the number. And if it is odd, then it returns negative 1. So if I given, let's say, 5, then I would get 4 as return. Now if I given 4, the same thing, I will get 5 as an output, and then if I give 5, I will get 4 as an output, and if I give that, I will get 5 as an output. Okay, the AArch64 translation uses conditional select instead of branching to implement the if-else statement. The input num is in WQ. Input num is in WQ and is also returned in WQ as the output. Flip-flop. Flip-flop. Tests for parity by setting the P state flag to W0 and 1. W0 and 1. Okay. Tests. Uh, test singular bit. What does this do? It tests this and adds. Wait. Yeah. It finds the and for this and sets it to the P state register. And after that, it subtracts 1 from the 0th register and stores the result in the first register, and then it conditionally selects and increases. It sees not equal if W1 and W2 are not equal, then it stores the value in the 0th register. If they are not equal, then it stores the value of the 0th register in the 0th register. Otherwise, it stores the value of the first register in the 0th register. Okay. This works because instead of testing if the function is even with division remain remainders as in the C code, number divided by 2 equals negative. The assembly does a conditional bitwise AND with the first 0x1 register, because the least significant bit will always be 0 for an even number and 1 for an odd number in binary. The value W0 is 1 minus 1 is placed in W1 if num is odd. Yes, if num is odd, then 1 is placed in this. Num is odd, which means the Z flag in P state is 0. Then, if it is odd, then the Z flag will be 0. Will be 0. The value this is placed in, yeah, 1 will be 0 because the first 0 and 1 is 0. 0 and 1 is 0. Then W0 is set to the value of W1. Yes, otherwise, if num is even, then Z flag is 1 and we do some things. Should charge. I'm back. Is my stream lagging? Here. Well, it is stuck. It is not to the mark, not in the present. This is just not acceptable. The quality of the stream. Quality of the stream. So it is actually lagging. And it is lagging on Twitch. And is it? Let's. Yeah, it is actually like. No, no, the mouse is working just fine in Twitch. Yep. And on YouTube, I stopped the stream. And is it? Let's. Yep, that is fine. Now, special instructions. There are a few instructions that do not fit into any of the previous categories. They are used to request operating system services and access advanced CPU features. So we can tell the operating system kernel to do stuff for us or advanced CPU features. Count leading zeros. Count leading zeros, count leading sign bits. These instructions count the number of leading zeros in the operand register or the number of leading zeros sign bits, and it stores the result in a destination register. This is the destination register. This is the operand register. Now we have option, and then this is the destination register, and this is the operand register. Shit. Register, 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 register. Um, count leading zeros and count leading sign bits. Now operations, count the leading zeros of Rn, count the leading sign bits. What does it mean to count the leading sign bits? Leading sign bits are in the front and leading zeros are also in the front. So this counts leading zeros and this counts leading ones or zeros as accessing the P state register. These two instructions allow the programmer to access the status bits of the CPSR and SPSR. Move status to register, move status to move register to status. What does this do? Okay, these two instructions allow the programmer to access the status bits in the CPSR and SPSR status bits of these two. And what are these two? Let's see. Move status to register. Move status. Move into register the status and move into status the values of register. So we have destination here, move into register. the field, this field, yes, field. Okay, we can access all the p state values, not just the four condition flags, but to access the status bits of these two, CPSR and SPSR, signed program state register and C program state register. The optional fields is any one of these condition flags, input bits, interrupt bits, current L, current exception level, PAN, privileged access, never. Okay, ARM version 8.1 only. Yes, I am using the latest ARM version, I think, in the Mac. Then UAO, user access override. The optional condition can be any of the codes from the table 3.2 specifying conditional execution. The optional condition can be any of the code from table 312 specifying any condition. Well, we don't have a condition here, do we? Now, examples, we can get the p state from the bits, the p state bits from the p state into a register or from a register into the p state. Now, the flags is the only p state field guaranteed to be accessible at the lower execution state. ELO, which is unprivileged and where applications are intended to be run. Now, this gets the value of this p state flags into the zeroth register, and then it finds the AND of the zeroth register and 0, which is like basically clearing the flags, yes. Then it stores the value of the zeroth register into the flag. Superior call, that is what we use to access the operating system. The following instruction allows a program to perform a system call to request operating system services. As we see, supervisor call. In Linux, the system calls are documented in section 2 of the online manual. Each system has a unique ID which can vary from one computer architecture to the next, or from one operating system to another. On Linux, it is generally better to make system calls by using the corresponding C library functions rather than calling them directly from the assembly. That makes sense. This is because the C library function may perform additional work before or after making the system call. For instance, the exit library function may invoke other functions to clearly shut down the program before it performs the exit system call number, and syscall. The system call is encoded in the instruction. The operating system may examine it to determine which operating system service is being requested. In Linux, syscall number should always be 0. The system call number is passed in the eighth register, and 6 other parameters can be passed on to 0th till the 5th register. As we see, request operating system service, perform software interrupt. Now, in the read only section of a program, we are storing a thing, a label, message, which stores a string, which is that this. She sells seashells by the seashore. Ah, didn't got me. She sells seashells by the seashore. 39 bytes. Okay. In the text section, we have a label called main, which is global and whose type is function. And then in the main, we first store the frame pointer and the link register onto the stack and increase the stack, that is just subtract some value from the stack. Then we move the value 1 into the zeroth register. then the address of message label into the first register, and now number 39, load number of bytes to write, is into the zeroth register. File descriptor 1 is standard output, and then we move x8 8 into the value 64, which is to write on the screen, write function in the 8th register, and then svc 0 system call invoked. After that, we move value 0 into the 0th register, get the frame pointer and the linked register back from the stack, and also get the stack back, and then we return. That is okay. We have done that in the past. Then this instruction does nothing except waste execution time. Nope. Just nope. No operation. Effect, no operation. That is just crazy. Move some value into the 0th register, then loop over nope, 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 and then subtract 1 from the 0th register, this, and compare 0 and this. And if this is greater, the content of the 0th register is greater, which it is, decrement counter. Oh, if this is greater than the content of this, then oh, if it is greater, then loop. And at the point when it becomes -1, this counter, then the loop will end. Okay. Now we are getting to the end of this chapter. Pretty close, I would say. This chapter and alphabetized list of AArch64 instructions. This chapter and the previous one introduced the core set of AArch64 instructions. Most of these instructions were introduced with the very first AArch64 processor. There are more architectural extensions that provide special instructions for use for uses such as cryptography. There are also additional instructions that compute floating point operations called vector floating point VFP. I don't know vector floating point. I know how we can store floating point in single and double precision. Single precision uses 32 bits to store a floating point number, and double precision uses 64-bit. And neon is a extension to the ARM architecture, to the ARch64 architecture, which is used by MacBook. The instruction introduced so far are these. We can just see, and we can come back whenever we want them. And now chapter summary, and then exercise. 10 exercises. Let's try to do them. First, chapter summary. The ARch64 instruction set architecture includes 31 general purpose registers and 4 basic instruction types. This chapter introduced the instructions used for moving data from one register to another, performing computational operations with 2 source operands and 1 destination register, multiplication and division, performing comparisons, performing special operations. Most of the data processing instructions are 3 address instructions because they involve 2 source operands. 3 address instructions because they involve 2 source operands and produce 1 result. For most instructions, the second source operand can be a register or a rotated or shifted register or an immediate value. This flexibility results in a relatively powerful assembly language. Now on to the exercise. If 0th register initially contains 1, what will it contain after the third instruction in the sequence below? Okay. So I add 1 to the contents of the 0th register, store that value in the 0th register. Therefore, we have 2 into the 0 in the 0th register. Then I move the value of the 0th register in the first register. Now the 0 and the first both contain the value 2, and then I add. Okay, this is good. Then I add to the first register, which contains 2, add to 2 the contents of zeroth register, that is 2, that is 2 is 1 0, after left shifting it by 1 bit, that is, so 2 is 1 0, and if we left shift 1 0 we get 1 0 0, and 1 0 0 means 4, so we add 4 to 2 to get 6, so at the end we will have 6, and 6 is 1 1 0. Now what will 0, okay, let's just check, just in case, check with chat GPT what the heck is going on. Yo, Technoblade, is the answer 6? Let's analyze step by step. Assuming this contains this, instruction 3, yes, then it started containing 2, then this also, and 6, yep, final answer yes is 6. Okay, what will 0 and x1 contain after each of the following instructions? Give your answer in base 10. Okay, okay. Move 1 to the 0th register. Okay, move, okay, hexadecimal 20 into the first register. Hexadecimal 20 is 32. Yep. Move 32, yes, 32 into the first register. Then OR the contents of 0th and first register. Skill you draw. Okay, first I will try to do this in mind and see if I get the correct answer. If don't, then we will move on to Excalibur. Now, or this and this. So for 32, I have, for 1, I have 1, and okay, so I will have 33. After this, I will have 33 in the first register. And then left shift the contents of the first register by 2. So 33, I have two 1 bits, 64 and 128, and 1 becomes 2, 4, 128 plus 4. That is 132. At this point, I have 132 in the first register. Then I OR the contents of 0th and first 132, basically adding 1 to it. Therefore, I will get 133. And then I XOR exclusive OR the contents of 0th and first register, exclusive OR only one of them. So I will get 132 in the 0th register, and then left shift the value of the 0th register 3 times. No, logical shift right the value of the 0th register in the 3 times and store it in the into the 0th, into the first register. So 3 times it says of the contents of the 0th register. Okay, 3 times, that will go out of range, and the other one will become 128, and then 64, 32, 16. I will have 16 in the first register. This is my initial thing. Uh, that x1 will have 16, and x0 will have 132. And let's see. Let's see. This is going to be fun. Is the answer 132 in x0 and what did I say? 32 in x1. Just say yes or no. Yes. Okay, the answer is correct. What is the difference between logical shift right and arithmetic shift right? Well, when we do logical shift right n times, let's say, then the least significant n bits are shifted and lost, and the most significant n bits, which are now empty, will be replaced by 0. But in arithmetic shift right, we still lose the least significant n bits, but the most significant n bits will be replaced by whatever is the was the original signed bit, which original sign bit. That is, if the number is negative, then all of those bits will become 1, and if the number was positive, all of those bits will become 0. That is the answer for this. Now, write instructions to load the numbers stored at address num1 and address num2. Add them together and store the result in num sum. Use only this and this. Okay, so write instructions to load values stored in num1 and num2 and add them and store them. Okay, okay, whatever. Chapter 4. This is pretty basic stuff. Very, very basic. Very, very basic. Very, 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 very. Dot text, and in the dot text section, we will define num1, which will store a byte or a word. Let's say a word, which will store a word long integer, which is, let's say, this big number. And we will have another label called num2, which will also store a word long integer, and that will be this. And now we will have num sum label, which will also store a word and which is initially just 0. Now in the dot, shit, I'm stupid. In the text section, and this is supposed to be in the dot data section. And now here, first, yes, we define that we have uh, a thing global label called main, and we can also align like good people that we are not, but pretend to be good. And then in the dot, in the main section, we first store pair, the frame pointer, and the link register into onto the stack, and also update the stack by making space for two 64-bit values. Oh shit, this is supposed to be 29 register. And then what do? I have to get the address of all these variables. Wait, I can only use two. Uh, 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 use only x0 and x1. Uh, that is doable. You know how? Like this. First, I get the page address into the zeroth register of num1 by doing this, and then add the offset, page offset, just like that. And then I load the value into the zeroth register, whose address is in the zeroth register. I load the value in the first register whose address is in the zeroth register. And so I have the first number, num1, in the first register. Now I want to get the second number. How can I do that? Or you know what? I can simply do this, um, this. That is crazy. And now I want to get the address into the first register of num2. For that, I first get the page address and then I add the offset, page offset. And then I do the same thing that I did with the zeroth register. Yep, now I have all both of the values and I will store the result in the zeroth register, the summation of first and zero. Yes. And then I have to load it back. So I will get the address into the first register num sum. For that, I first get the page address, then add the offset num sum page offset, and then I store the value in the zeroth register to the memory location whose address is there. And then, like good people, we get back the frame pointer and the stack pointer, the frame pointer and the link register contents, and also update the stack pointer and then return. Before return, let me put move something into the zeroth register will be the exit value of this function, which is the number 420 clang chapter 4. And oh, oh, my bad. I'm using LDR instead of LDP to load a pair. My bad. Oh, oh, my like literal bad. I want to see the output. So for that, I should not do this. Just I will see the output here. Now, going down out and echo. There's any question and 189. How to see the exit code of a program in Mac. Dollar question mark. That is what I used. Dollar question mark. Hmm. 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 Okay, instead of giving out the output in the DA, I can use the printf function provided by the C library to do it. And for that, I have to get a string which will store as keys, and the ASCIIs will store the value. The sum is percent d backslash n. And now this is crazy. I have the limitation that I can only use two registers, the zeroth and the first. Now, at this point, I stored the result in the numsum place, and now I have to pass two arguments to the printf function. The first argument is passed in the zeroth register, So zeroth register should store the address, and the second argument, that is the zeroth register should store the address of the string, and the second argument will be passed in the stack pointer. So let me store, no wait, in the stack pointer or at the location that is at the stack pointer, at the location like I did yesterday. Why am I being stupid? So store the contents of the zeroth register at the stack pointer, but update the stack pointer by 4 first, and it's minus by 4, and then do this, okay, and then store in the numsum location, and after that update the zeroth register to store the address for the string. And for that I get the address of the page, the string page, then I add to the zeroth register the string page offset, and then just bl the printf function, branch link call the printf function. This should work. And like good people, I first subtract, nope, add to the stack pointer and store in the stack pointer and add to the stack pointer the value 4. Why the value 4? Because I minused in here the value 4. Clang, bus. How can I be stupid here? I'm working with a stack pointer. Store the contents of 0. Okay, I need 8 bytes, don't I? Because I'm using x0 here. My bad. X0 here. I can use W0, but let's just go with X, right? And 8 here, and okay. This should have worked. This time I was hoping it to work. Hmm, okay. Where is the error part happening? Hmm. Whenever I manipulate the stack pointer, it just messes up. Store the value of this into this, into the location which is stored at here. This is no different from what is happening right here in the first command. Absolutely no difference. Wait, is it because of the printf function? I am providing the address in the zeroth register, the address of the string in the zeroth register, and then on the stack I also have the value. Let's remove some things and see which ones cause error. Is the number too big? Nah, it can be too big because maybe it is. Let me use the whole quadrant that is 64 bits. Well, I don't think that is the problem. Error, bus error. Hmm. What is it? Why don't call the printf function and then do I get the error? No. So is this causing the error? Let's see. So and out. Okay, the printf function is causing the error. When I call printf, that is causing the error. Why is that causing error? The pointer stack has the address. A stack contains the address of the memory location, which stores the value, the sum. Hmm. I called printf before. Pass in the string, pass in the string, and then I add to the stack. I added to the. Yesterday was a pretty good day. I added to the stack because I had already taken quite a bit, like here. Okay. Let me do it in two steps, like I did yesterday. Subtract from the stack pointer 8, and then just store in the stack pointer. Um, this doesn't seem much different from what I was doing before. So, yeah, that's still the same. Chapter 4. Why chapter 4? That is the chapter of the book that we are using for this. Stack pointer. Where am I messing up? Everything is going fine. The zeroth register has the content for the string, and string is null terminated as keys. Okay, let's remove the %d thing and then try to call it still. What is the problem? Block. Why can't you make it work? Hmm, Let's just go bonkers and do this, and then at the end do this. I don't know. Maybe that is the thing causing the problem. That was things were overlapping in the stack. Stupid, stupid I am. Things were overlapping in the stack. That was the problem. Things were overlapping in the stack. That was the problem. And now we have the answer. It is working now. Okay, so we did this one. Now, given the following variable definitions, where do you know the values of x and y? Where do you, where you do not know the values of x and y, write a short sequence of ARM assembly instructions to load the two numbers, compare them, and move the largest number into the register 0. That is pretty basic stuff, just what we did here, like loading the values. In this part, we had the values, and then what we have to do is compare the values and of this and this, and if greater, then load that. That would be um, compare conditional uh, select into the register 0 if 0 is greater, and if this is greater and greater, then this should be this should, now the 0th register has the value that is greater. The 0th register has the greater value. Will this work? This should work. Yep, this should work. Compare, then select based on this. Oh, I don't even use that. Don't even have to use that. And then store value in the stack pointer into the location of the first. No, don't have to do that. And then get the address of the string, call the printf function, and get the hell out of here. Right. The greater value is this. This is that. This is the greater value, which is crazy stuff. Let's say that this is 5 now. There was a mistake. I just saw. What was it? Yep, in the string. Uh, Greater value is clang this shit out of here, and okay, it is only printing the first value no matter what. Hmm. Hmm. Conditional select. I am using it properly. Compare select. Conditional select. I am using it properly. Conditional select. Right. I am using it properly. I would say if condition, then this goes into this. And where are the examples? Yep, here. If greater than GE, I have to use compare before that. Compare this and this. Now this should work, and if I make this 9, I should get a string, a number that starts with 9. 9. This function, yeah, it now works. Now moving on to the next question, which is this: assuming that A is stored in register 0 and B is stored in register 1, show that ARM64 assembly code that is equivalent to the following code. Show the ARM64 assembly code that is equivalent to the following code if A and 1. That is, if A is 1, then put A equal to negative A, else put B equal to negative B. In a single instruction, show assembly code. Okay, if A A and 1, I can do compare negative, and the answer should be this: compare C uh, inverse the contents of zeroth register if this condition is true. And what is the condition? Condition is um, compare the contents of this and 1. Well, not 1, but yeah, 1. 1 would do. 1. And the condition is EQ if they are equal. Now, else, I have to use else. So I can just use here else. Mm, compare, add, see, add 7. I have to add 7 to it. How can I add this much? So I can increase, but how can I add 7? Do I have to use compare, increase 7 times? That would be crazy. If I were to do compare, increase 7 times. How do I add? Yo, oh, 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 yep, compare, increase. I can only add 1. Ah, compare, select, increase. I can make that register the same. Yeah, compare, select. I will have to use this multiple times if it is not equal. 7 times to be exact. 2, 3, 4, 5, 6, 7, 8. Not 8, 7. Give me the pistol. Write a loop to count the numbers of bits in x0 that are set to 1. It has only been 1 hour and 30 minutes. That is crazy. I thought it is going to be 2 hours. That has been 2 hours. Write a loop to count the number of bits in x0 that are equal to 1. Use any other registers that are necessary. Okay, the dot. No, I don't need any data section thingy. In the text section, I have a global function called main, and we align just like good people. And then the main, we will not be storing a stack pointer. Let's just do it. Store pair contents of 29 and the 30th register onto the stack, and also in get new values in the stack. And now let's move a number in the zeroth register which you want to check. Let's say the number is this 10, and I'm using binary here. Okay, I can use just 64 of these. Okay, now I have to write a function which will count the number of bits. Okay, for that, let's just first we will be using zeroth, the first register as the count, right? Which is which will start at 0 and then it will increase. Now, loop. I want to loop 64 times. How do I do that? I move 64 and yeah, okay. So first, what I do is I compare the contents of the second register with 0. And if it is 0, what do I do? And branch if they are equal to end loop. Otherwise, the code here and at the end I do subtract and store in the second register and subtract from the second register value 1 at the end of the loop. Yes, that is what I do. And end loop is something like this. It just loads in the stack point, no, the frame pointer and the link register back from the stack pointer and gets the stack pointer back to its original value. And let me go to the washroom. A minute. I'll be back. Right back. Okay. And okay, now we are here. Now the main juice of the loop function. First, it will check, uh, compare. I want to see if the LSB is 0 or not, if it is 1 or not. So what do? I do and Ands, is that what I do? Ands the contents of the zeroth register and one. No, not the one register, but one literal one value. And the result is in the flags, flags. Okay. Now, after that, if conditional increase, what I want to increase the contents of the first register when I want to increase it when um how does the ands update? How does the and function update uh, the program flags, the p state register? How does it updates them? Nah, I'm being stupid here. Somewhere I am being stupid here. The ands also takes a destination register where the value will be stored. Okay, and then after finding the and with this, I can compare that value with one and then okay, store it in the third register. I think this can be optimized somewhere and don't update the program flags. Then compare the contents of the third register and one. And now if the LSB of the zeroth register is one, then I should get equal. So increase when equal and then logical right shift, logical shift right the contents of zeroth register by one. And then at the end, I would like to print. Gotta call the printf function. And hello there. Dot data string label which will contain ASCIIs and the ASCIIs will be number of ones is %d and the new line. Now this end loop will have all the answers. So before anything, I want to call the printf function there. So I will get the address in the zeroth register. For that, I will get the address of this page first and then add to it the offset of the string page offset. Okay, and then I have to provide the number in the stack. For that, I load the value of 0 1 into the stack pointer plus no subtract 16, and then before leaving everything else I yep first I then bl call the printf function from here and then get back the stack pointer to its original thing by adding to the stack pointer and storing to the stack pointer the number 16. So can't I use this? What are the errors? Okay, expected compatible register or logical immediate. Okay, so I will have to see how to provide binary. Okay, error invalid operand for instruction. Compare and increase. Invalid operand for okay. Okay, compare increase conditional increment, compare increase of operation 2. Okay, compare an increase, compare and increase. Ah, okay, okay, that makes sense, I guess. So, yep, I can just use decimal values, some spooky decimal value number, and then this is the thing giving me error. So now it should not, because I have provided our destination address. And what was the other thing giving me error? It was this. Here also I have to provide a destination address. That should work. At least compile. Okay. Expected compatible register or logical immediate. Is that too much? Is that too much of a value? Move that into that. Is that too much of a value in immediate value? Too much of an immediate value? Oh, was that the problem in the first ca case when I was providing it something like this? This, okay, some number, a big number, and literal pool, unknown token in expression. It does not know equal to. Let me just provide it a smaller value. That should work. Is that how much ones are there in that singular register? And chapter 4 and where am I here? Just let me give a single one, and I should see one, but I do not see one. I just see the same number even though I changed the thing that I am operating on. So is it not? Here is the problem then, it seems. So I compare the contents of the third register and 1. And if they are equal, I increment the first register and store the contents in the first register. That is the destination register. Okay, and here, and I am doing and for the third register, I'm storing it in the third register, and I am doing and for the third zeroth register and number 1. This should work. This should work. This should work. This should work. And I'm also doing logical right shifting to change the LSB every time by 1. Subtracting 1 from 2 also, so that the loop ends at some point. What if I simply just, oh shit, I'm so stupid. This has to be stored str. Why am I loading anything? This has to be, ah, shit. chapter 4 and okay, the number of ones in 63 should be 5. 63 should be 5. 5, 63 is 1. Oh, this 64, 0. Am I not doing the left shifty thing? The right shift thing properly. Give me the pistol. Logical right shift. This. Hmm. It should work. Logical right shift. This. This is being logically right shifted. The contents of the zeroth register are being logically right shifted and stored back in itself. And here I'm doing comparing one, ANDing 1 with 0, and if the LSB of zeroth register value is 1, then I should get a 1 in the third register. Then I am comparing that 1, com I'm seeing if the third register has 1 or not. What do I give 2? I should get, I think I will get 0 for 2 also. Yeah, so I recognize the problem. The problem is with this LSR, logical left shift, logical shift right, shifting right, shifting right. Why is it not working? It should work. First, I check, and after checking and increasing the value of the first register, then I shift right so that when I check the next time, I will have the next bit in the zeroth register as the new LSB. Something is not adding up. There seems to be some there seems to be some mistake. Hmm, Logical shift right is should shift right the width. It is not working. It is not working. Why is it not working? Logical shift right. Just did that here. Understood. LSR, LSR, LSR. Shift and rotate LSR logical shift. No example of LSR. Okay, here, here, here. LSR. The content of this. The number this. So do I have to provide 1? Cannot use immediate value here. Fucking hell. I think I can use. Let's just do it this way anyway. Or I will store the number 1 in the fourth register and give the fourth register here. Now, if I see 1, then we are all good. And if I see 0, then some debugging, some debugging. Um, I think we can ask ChatGPT what the heck is wrong with this. What is wrong with this? This this code uh, has to find the number of ones in a number, and it seems like it is not performing the LSR. Okay, there are a few issues in your ARM assembly language that prevent it from correctly counting number of ones in a number. And here are the problems: infinite loop or incorrect loop implementation. The loop condition checks 0 compare, but is not initialized to 64. It is initialized to 64 here, right here. Okay, infinite. Or however, the actual zeroth register should control the loop termination. Otherwise, it keeps shifting even after all the bits are processed. Becomes zero instead of using a fixed iteration count. That makes sense. Instead of doing this and then comparing this with zero, I can compare the zeroth register content. Okay, and then incorrect stack allocation for printf. Stores one on the stack, but the offset is not stored before calling printf. Properly adjust the stack. Let, let me do this. Sub from stack pointer and add into stack pointer number 16. Okay, incorrect printf call. The argument to printf is stored on the stack, but printf expects the argument in parent action one on the stack. No, the printf is fine. Shift by right one, yeah. Shift by right one, LSR. Yeah, yeah, yeah. That is everything is fine. Everything is fine. Everything. 1 into 2, 2 into 1, and BL printf, BL printf. And yes, I'm storing here, which is yes, I want to store. That's what I want to do. And then LSR is also fine. And then adding and checking if equal, and then increasing one and storing into one, and LSR is 0. Adding the contents of 0. Let's see. No, I don't have to do this. Just recompile and run. Let's see if it works. Look, das funktioniert nicht. And if I do this one, then it will work. No, well, not work, but it will give me one. I guess, yep, it does give me one. And if I do this, make this 3, which will be 1 1 in binary, I will still get 1. It is not increasing after 1. Why is that? It is not increasing after one conditional increases. Do I have to like clear the values in the third register into the third zero? There was something. Um, I want to see one one. No, I want to see two at the output and percent d storing the value of zero first register at the memory location whose address is at the stack, the top of the stack. The value is also in the first register as the string in the zeroth register, increasing, comparing, moving. First I move zero into the third register to just overwrite and have a new beginning, fresh start. Then I store into the third register the AND of 0 and 1. Okay, the problem seems to be with LSR, logical shift right. Let's just in case use LSL, logical shift left, to see if it works. Or is the problem in the printing, in the printing thingy? So before that, I can move into the first register the value, let's say 100, and lang 100. Nope, printing is just fine. That is just the contents of the zeroth register, the contents of the first register. Yeah, what the heck is going on? Oh, it has been 2 hours. Okay, quite a long stream. Not quite a long, but there. Okay, we have to do complete at least this, and I will not be streaming for 3 to 4 days. I will be going outside to IIT Roorkee because there is a some event there which I want to attend. And here, what is here? Branch link. What is the problem? Move. Uh, this is working just fine for the first LSB, but then this does not seem to be shifting as it should. Or is it not storing that value? Yes, it is storing the 3 as binary. Of course, there is no other way for it to store it. Is it because I'm working with binary, therefore I have to provide numbers in binary? Is that it? 0B1? Mhm. I don't know. 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 Nah, let's just see. Um, I don't know. And I think I will get an error. Um, oh, um, don't, 27, get out of here. Okay. Okay, so for one, I should get one. But let's say for 10, I should also get one. what happens here if the condition is false? Does it not increase or does it initialize to 0? Conditional increase here, conditional increment. Oh, this the same thing is stored. The no change, no change, no change, no change, no change, no change, no change. If the contents of the third register are equal to B1, equal to what? And what are the contents of the third register? The content of the third register are the AND of 1 and 0. Sign extend. Mm, 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 mm. Okay, I will figure it out. We will figure it out in the next stream, I guess. And the next stream will be 3 to 4 days from now. And good luck. Bye. We will live another day and meet.